we're going to move away from adding water to now adding alcohols to aldehydes and ketones. So with this reaction, we're going to do this under acid catalysis. And I'm just using methanol as the alcohol that I'm adding, but we can add any alcohol. And the first step, you can think about this very similarly to how we added water. So I'm going to draw the hydrogen up here by the oxygen and the OCH3 group down here. And just think about adding OCH3 and hydrogen across that pi bond. So we've added the proton from methanol to the oxygen, and then we've bonded an OCH3 group to that carbon that was the carbonyl carbon. Right, this product here is known as a hemiacetal. And what that is it's a carbon that has one OH and one OR group attached. And that's what we have right here, an OH and an OCH3 is the OR group. Now in this particular process, there's two steps that happen. So the hemiacetal generally doesn't hang around for long. This will continue to react with the methanol. And what will happen is the OCH3 will replace the OH. So let's draw that product. And we'll see how all of this happens in the mechanism in just a bit. So we have our first OCH3 that was added. Our second OCH3. And then we have the water. So that was the byproduct of the reaction. This product, where we have the two ether groups attached to the oxygen, this is known as an acetal. So that's a carbon with two OR groups. This whole process is an equilibrium process to convert an aldehyde or ketone to an acetal. But water is a product that's released in the reaction. So a common way to drive this reaction to the right is by removing water as it's formed. Think back to general chemistry when you talked about Le Chatelier's principle and disturbing an equilibrium. So if you continually pull out a product from the reaction, that's going to pull the equilibrium in that direction to try to reestablish the ideal equilibrium. So if we keep removing water as it's formed, it's going to drive this reaction to the right. This reaction involves the two steps, hemiacetal formation and then acetal formation. And we're going to take a look at both steps along with the reaction mechanism. All right, so we're going to start with step one, which is the hemiacetal formation. Okay, so here we have the ketone, and this reaction is done under acidic conditions, and we saw how the hydration took place under acidic conditions, and it's very, very similar. So the first thing we'll do is react the carbonyl with the acid. And I'm going to say this again, and I'll probably say it 50 times. Anytime you have a carbonyl and acid, always protonate the carbonyl oxygen first. Okay, so now we have the activated carbonyl. And that means it's extra reactive. All right, so now that we have this extra reactive carbonyl, we can use methanol as a nucleophile. So I'm going to take the lone pair on methanol's oxygen and draw a curved arrow to the carbonyl carbon, and then push a pair of electrons up onto that oxygen, making it neutral. So there's my OH. And then I have O, CH3. There's still a hydrogen on that oxygen, and it bears a positive charge. All right, now we need to get that hydrogen off of there. So this step, you can use anything in the reaction that has a lone pair. You can use a molecule of methanol. You can actually use a ketone with its lone pair. Myself, I like to just use B to be generic, just to say anything in that reaction mixture with a lone pair can do this. The base will come and take this proton and put the second lone pair on the oxygen. So I'm going to leave those lone pairs implied, plus we get the BH+. So that's how we get the hemiacetal. All right, so now step 2, we need to convert the hemiacetal to the acetal. So let's redraw our hemiacetal. All right, what we're basically doing is trying to get rid of the OH and add the methanol. So if we want to make OH a leaving group to get rid of it, we want to protonate it. So that's going to be my first step. We have acid around. The acid will protonate the alcohol. Right. Anytime we have OH2 plus attached to our molecule, that means water is attached. Water would rather be off of the molecule, hanging out as just neutral water. So that is a great leaving group. So what I'm going to do is use a lone pair on this methoxyoxygen. I'll push that down, which will assist me in pushing away the water as a leaving group. So now I end up with a double bond to the OCH3 and a positive charge, plus the water that I lost. All right, so what I effectively have right here is another activated carbonyl that wants to accept the nucleophile. So this is when methanol adds. So I'm going to use the methanol. Add that to the carbonyl carbon. So on one side, I'll end up with just an OCH3. On the other, from the methanol that added, I have OCH3 and a proton attached. So now, just like we did up here when we needed to get rid of the proton, I'm just going to use a B for a base. Take that proton off. And that leaves me with my acetal. One thing you will sometimes see done in this mechanism is a shortcut taken, where you start from this intermediate right here and just show an intramolecular proton transfer. And basically transferring the proton from this OH to this OH. And if that's shown with mechanism arrows, you would use a lone pair on this oxygen come and grab this hydrogen, putting the lone pair on this oxygen. So when you grab that extra hydrogen over here, that gives you the OH2 plus and the neutral OCH3. So that's kind of a shortcut that's commonly taken, and it is acceptable, although it's thought that the true mechanism is this two-step process where you take the proton off and then put the new proton on.